All right. Good evening and good morning, everybody, and thank you for joining us at this International Institute for Fibre Composites in Construction webinar for the Best PhD Thesis Awards for 2020. We are in unusual times, so this is quite a unique event for us, and I hopefully it will be an enjoyable an hour or so while we listen to the shortlisted applicants for the Best PhD Thesis Awards. Just a little bit of a refresher in terms of what the objective of the IIFC Best Thesis Awards are. It's to promote the high quality research on FRP composites in construction, and the IIFC has established this Best Thesis Award over several years. So, and the award will entail the winner receiving an award certificate, a cash prize, plus 2 years complimentary IIFC membership, and potential to be invited to prepare a short article for publication in FRP International. So we received several applications, and the selection panel and the judges for this year are as follows. So I've chaired the Best Thesis Award category. Professor Karim Benzati also worked on the committee to shortlist applicants, and we have Professor Joan Correa and Professor Alpa Ilke and Professor Scott Smith as part of the presentation judging panel today. And we are joined by our 4 shortlisted candidates. So firstly, I'd like to congratulate you all for being shortlisted to this stage, and also for making yourselves available to present your seminar online in this format. And so our 4 presenters are Dr. Enrique Del Rey Castillo from the University of Auckland, and his presentation will be on fibre rupture failure mode of FRP spike anchors. Our second presenter will be Dr. Omar Saleh Al-Jarame from the University of Southern Queensland, Australia, and his presentation will be on compressive behaviour of hollow concrete columns reinforced with GFRP bars. Our third presenter will be from Dr. Marco Rossini from the University of Miami, and his presentation is on FRP reinforcement for pre-stressed concrete applications. And our fourth presenter, Dr. Jiwan Wang from Tsinghua University in China, and his presentation will be on reinforced concrete columns reinforced with FCCCR, axial compressive behaviour and seismic performance. So the way that we will go through these presentations is that the first presenter will have about 20 minutes or so for his presentation, and then we will have time for questions. If during the presentation you would like to post your questions, and that is fine, feel free to use that facility in the chat function. Or if you are happy to just wait for your questions to the question time, that's fine as well. So we will take questions either that have been posted through the chat or online. So without further ado, I'd like to invite Dr. Enrique Del Rey to present his presentation. So I will stop sharing my screen now, Enrique, and allow you to have that access. So welcome. Thank you.
Thank you, Rebecca. All right. Can you all see my screen?
Yes, we can. Thank you.
Good. Thank you. So first, before I start, I want to add a disclaimer. My 2-year-old is sleeping in the room next door. So if you start to hear screaming and crying, I apologize in advance. Hopefully I will not wake her up. So my name is Enrique Del Rey Castillo. I did my PhD at the University of Auckland in New Zealand, and my supervisors were Mike Griffith from Adelaide and Jason Ingham from Auckland. During my PhD, I investigated the fiber rupture failure mode of FRP anchors, and I developed design equations to predict the capacity, the load capacity. Now, the front end of the presentation is very quick because I assume that we all know what FRP is and how it's used. In this particular application, externally bonded reinforcement. The FRP is bonded to the external surface of the concrete element to enhance the flexural capacity or the shear capacity or whatever we may need to do. I like to use this figure because I think it's very useful to explain how to use FRP. It's also one of the most common applications and one of the most well-researched applications is shear strengthening of beams in case we don't have enough steel wraps, they are too far apart, they are too small. Now, the best solution is to fully grab the beam around with FRP. Now, the problem is in most of the cases, this is not possible because we have something that prevents the beam to be fully grabbed. In this case, we have the slab on top. In that case, what is going to happen is the FRP will debond from the concrete, breaking the top layer at very low strains. So we are not using the material efficiently. One way to overcome that premature debonding failure is FRP anchors, which are just bundles of fibers that are soaked into epoxy, and then one end is introduced into the concrete, into the slab in this case, if we are using straight anchors, and the other end is fan out and bonded to the FRP sheet behind. So we have the dowel inside the concrete and the fan outside. Now, we have two broad categories of FRP anchors. One is straight anchor, when the dowel goes straight, so the fibers are only bent in this direction. And bent anchors, when the anchor goes in an angle into the beam in this case. To explain this better, I have this figure in here, where I have all the different parts in different colors. So we have in green the dowel, which is introduced into the concrete, whether we have straight anchors at the top or bent anchors at the bottom. And the diameter and the embedment depth are going to determine the capacity of the anchor related to the dowel. Then we have the fan portion, where all the fibers are fan out and bonded to the sheet behind. And we can make wide anchors or we can make narrow anchors. And that width is determined by fanning angle alpha, which I specify as half of the fan, and you will see why in a few minutes. And then the part of the anchor where the fibers transition from the dowel into the fan is usually called the key portion, because it's where all the fibers will break if we have fiber rupture failure mode. Now, in addition to the diameter and the embedment depth of the dowel, we have the fan dimensions and the insertion angle beta. So all of these parameters here at the bottom will determine the failure mode. This is how I started my PhD, to look at the different failure modes that we can observe in FRP anchors. On the left-hand side, these 6 in here, we have concrete-related failure modes for straight anchors at the top, bent anchors at the bottom, and the government parameters, which is the strength of the concrete, the depth of the dowel, the diameter, and the insertion angle beta there. But looking through the literature, I saw that there was a lot of research on this failure mode. And I thought, even though there were always space to do more research, I thought it was pretty well researched. Then looking at the next failure mode is fan to sheet debonding, where the fan debonds from the sheet in the background. And the parameters are the shear strength of the resin and the area of the fan. But I thought this was not really interesting to me, and it was a little bit not complex enough for a PhD project. So I focused on the fiber rupture failure mode, where all the fibers break, usually there in the key portion, whether we have straight or bent anchors. And the parameters are the strength of the FRP. You can also use the modulus of elasticity times the rupture strain, the area of the dowel, so how big the anchor is, fanning angle alpha, so how wide or how narrow that anchor is, and the insertion angle beta. So once I know what I wanted to do, I had to figure out how to do it. So I developed this testing setup. Is similar to the shear strengthening of a beam that we saw in the first slide, but upside down. So that beam at the bottom is the slab, where we have the anchor introduced. Then we have a concrete block at the top, which is the beam, and these two are not connected. Then we have the sheet wrapped around the block and the FRP bonded to the sheet and then introduced into the beam. And without spending too much time, because I don't have a lot of time, I basically lifted this block in vertical until the fibers broke in there, and I recorded the load. This is for straight anchors. On the right hand side, for bent anchors, similar approach, just the anchor is going straight into this block rather than, sorry, bent into this block rather than straight. So I spent a whole lot of time in the lab, getting my hands dirty, installing FRP, breaking FRP, and I ended up with 110 specimens, 72 for straight anchors and 38 for bent anchors. Now, in terms of fan angle alpha, I looked at 3 different angles, 15, 27, and 60. 27 because it's as wide as long. And then for straight anchors, I looked at different sizes from 14, this is dry cross-sectional area, by the way, from 14 square millimeters all the way to 168 square millimeters. However, for bent anchors, when I started to get to 84 square millimeters, the efficiency was very low, something like 40% or 45%. And talking to the engineers, the company I was working with, they told me that if it was so, the efficiency was so low, they wouldn't use it anyway because it wouldn't make sense from a business, from economical point of view. So I stopped there. That's why I have less specimens of bent anchors. So I recorded the load for all of these 110 specimens, and I started to look at the scientific background, at the theory of how the force is transferred from the sheet on the right-hand side to through the sheet, through the anchor, through the dowel, into the concrete on the left-hand side. So I started, my first hypothesis was, well, the force in the sheet has to be the same as the force in the dowel because we want equilibrium, right? If one of the two is higher, then it wouldn't be in equilibrium. And then I started to think, if we take the sheet and divide this sheet in a number of infinitesimal forces, and each of those infinitesimal forces corresponds to an infinitesimal force in the anchor, then each of these infinitesimal forces has a different alpha angle, alpha I call it here, Fi and alpha I. Each of these infinitesimal forces, Fi, will have a longitudinal component, Fn, and a transverse component, Ft. So I thought, right, all I have to do is to do the sum of all the longitudinal components, times 2 because I'm using only half of the anchor. And then you just integrate the area under the curve and you obtain the force. But my data was not matching this theory. So I started to look in more detail. I used digital image correlation, which I don't have a lot of time to describe, but basically you take pictures of the specimen as is elongated as you apply the load, and the pictures capture that movement, that elongation, and can translate it into strains. Now in these figures we have longitudinal or vertical strains on the left-hand side, transverse strains in the middle, and the rupture on the right-hand side. 2% red in tension, 2% blue in compression. Now, for virtually all the anchors, I got a huge concentration of stresses in this direction at the bottom of the anchor and pretty much nothing everywhere else, which makes sense, right? But that is not telling me why one anchor fails at one load, and if I make it bigger, the load is less. So what I did is look at the transverse direction. And I always, not always, but in most cases, I had these patterns of compression and tension coming from irregularities or asymmetries in the installation or in the load. And what I saw is that these patterns would always be reflected in the failure shape. So that got me thinking that, in fact, the strains in the transverse direction play a more important role, or as important, as the strains in the longitudinal direction. So I thought, well, as the anchor gets bigger, the load decreases for the same size. So wide anchors are less efficient. That means that for wide anchors, that factor is more important than for narrow anchors. And I came to the conclusion, without spending a lot of more time on this because I don't have the time, that if I do the summary of all the infinitesimal forces in the longitudinal direction minus all the infinitesimal forces in the transverse direction times 2, then my data match very well this hypothesis. So I was very happy with that. The problem is that this force transfer mechanism doesn't account for the 3D direction, for how big that double is. And from research and from my own experiments, I knew that a big anchor is less efficient. An anchor twice as big is not twice as strong. So I started to look at different options. I looked at many different hypotheses of how or why that could be. And I came across Mobius transformations, which, if I have to be honest with you, is really complex. It's fundamental mathematics. I had to go to the Faculty of Math to talk to a professor there to really understand what this was about. And long story short, these are used to map the complex unit circle into the real axis line. This is useful for how to do maps of the Earth, which is a sphere, into a map which is a 2D. And I thought this was fitting my purpose because this is the anchor fan. I have the dowel there at the bottom. And we need to figure out how all of the fibers in that circular shaped cross-section at the end of the dowel move into the top of the anchor fan, which is so narrow that can be assimilated as a line. And without going into all of the details of these mathematical equations, I ended up with an equation with the element in here for the Mobius transformation from the area of the dowel, then another one in here for the area under the curve of the longitudinal minus the transverse elements, the material properties, and then a number of variables, A, B, C, D, and E. And that matched the data very well. But we thought, my supervisors and I, we thought that this equation was a little bit too complex for engineering design. So we decided to simplify it a little bit. And we ended up using this equation, which is a little bit less accurate, but I think is much more user-friendly, where we have the area of the dowel to the power of B, then the material properties, and A. And we have a little factor in there to account for the width of the anchor. Now, looking at the statistical distributions and looking at the standard deviations and all of those things, I developed 3 equations, one for the average to predict the average value, one to predict the 95th percentile, the lower bound characteristic value, another one for the 99.87, which is a value sometimes used in FRP, both for straight anchors and bent anchors, and the only difference is those factors, the A and the B. So this is all well and looks good and everything, but while I was doing all of this testing in the lab, I thought, well, how applicable is this? I'm doing one test of one anchor in the lab. How applicable is this really when you have a structure, multiple anchors, FRP graphs, and all of that? So I decided to do a case study. And I decided to do a flexural strengthening of columns for 3 reasons. One, because there is no research. The only paper I could find by Professor Alper Ilki was using the same approach of longitudinal FRP, but not anchors. I think correct me if I'm wrong here, but I think he used NSM bars. So I thought it was a very innovative idea. The second reason is because shear strengthening of columns is very well known. We have been using it since the 90s. There is a lot of research. We know how it works. So it would be a good complement to be able to elevate not only the deformation capacity, but to be able to elevate the moment capacity as well. And the third, and arguably the most important reason, is that the company I was collaborating with had a few projects in which they were doing a similar thing, but based on engineering common sense, not based on any theory or any data. So it was going to be very useful for them. So basically, we bond the FRP in the longitudinal direction, in the vertical direction, and anchor it to the foundation or through the slabs in between floors. I designed 6 columns based on those from the, it's called Contec, the company that I was working with. And we built them in the lab, and I tested 1 without FRP, 5 with FRP. Now, there is a lot of information in here, but bear with me. The main objective was to check if I could calculate the moment capacity using section analysis. I could know the strain at which these anchors would break from my equations. So by using that strain in the equation, in the section analysis, I could calculate the moment. So I used in column 2 and 3, I used 3 anchors, 84 square millimeters. In column 2, no confinement, column 3, confinement to compare. There was no difference. Then I used another data set for anchors 112. But then for column 5 and 6, we decided that we wanted to break the sheet here, not the anchor, because the company thought that it was better, it was easier to repair if it failed. So we increased the number of anchors and their size, and we could calculate the moment as well. Finally, in column 6, I used a bond breaking layer at the bottom half meter, because we observed in these 4 columns, we observed high asymmetry, and the FRP would debond in the compression cycle by something similar to buckling, instead of the tension cycle by slowly debonding. Testing setup, nothing special, load at the top, axial load, and then lateral load. I measured the displacement of the load at the actuator point, and I used digital image correlation to see what was happening in the anchor area. We can see the anchors in there. I observed 3 behaviors or 3 stages. The first one, linear elastic, up to the point with when the FRP first debonded from the column in the back. Then an inelastic hardening. This is column 6, by the way, so you can see it's quite symmetric. In this stage, all the FRP debonded from the bottom all the way to the top until the first FRP rupture. So that's the peak point where the FRP ruptured for the first time, whether it was an anchor or a sheet. Then in stage 3, the FRP ruptured slowly, depending on the column, sometimes more slowly than others. And then when all the longitudinal FRP was broken, the as-built behavior was resumed, which summarizes to this trilinear behavior: linear elastic, inelastic hardening, and then as-built, which give us 2 points, the debond point and the peak point. Now, there is a lot of numbers in here, but don't try to read them, just listen to what I'm saying. R2K, by the way, is just using response 2000, is using moment curvature and section analysis. As we increased the amount of longitudinal FRP, the moment increased, both the debond moment and the peak moment. And I could calculate that quite well, I think. 6.2 difference, 6.6% difference. So I think it works. It's just section analysis, one with one more material with different properties, but it can capture the moment capacity. However, the drift is all wrong, because all of the plastic hinge theory and all the drift theory is based on reinforced concrete, steel and concrete. So it cannot capture the stiffer columns that result when you put FRP in it. And I am about to finish. If I had to say what I did during 3 years in 2 sentences, I would say that I developed new equations that allow to predict the fiber rupture failure mode of FRP anchors. Then I combined them with existing research by Scott Smith and Ravi with other failure modes, but that was not part of my PhD, so I left that out of this presentation. And then I developed a new innovative seismic strengthening scheme for reinforced concrete columns. Now, I think the work is quite highly cited. I published most of my research last year in 2019, but I am more proud of the impact that the research is having in the industry. The research is finding its way towards the ACI 440 document slowly. I have designed recommendations and courses for New Zealand engineers. We did some courses at the end of last year, very successful. I get emails and calls. Excuse me. I will continue. So that's something that makes me proud, and these are used in many projects. This is a coupling beam for shear walls, columns. This is a bridge to elevate the seismic capacity of the pier wall. And I published several conferences summarizing these practical uses. And that's all. Thank you.
Thank you, Enrique. That was very informative and really well presented. So I enjoyed listening to your presentation. So thank you for that.
Oh, thank you.
I would like to ask the audience if they have any questions, please, for Enrique. And maybe just remember to unmute your microphone. Maybe I'll start.
I'll ask a question, Rebecca, if you want.
Thank you, Kent.
You know me.
Yeah, I am afraid of your question, Kent.
No. Excellent presentation, Enrique. I was actually curious about something at the end. You were talking about the fact that the column drift behavior was not well predicted, and I didn't quite follow that. What's going on here? What is there? Why can't you predict this based on the stiffness of the anchor and what have you? Maybe I don't quite understand, because I certainly know R2K really well, and I'm pretty certain we should be able to do a good job with this.
Maybe I didn't crack the problem yet. Hopefully I will sometime. But basically the curve is stiffer, right? So if this is your normal reinforced concrete column, this is what you are going to have. And the equations or the theory that we use, at least here in New Zealand, are based on plasticity, on lumping the plasticity at the bottom, right? So if you have your curvature like this, you are lumping everything at the bottom. To do that, you need to calculate the plastic hinge length. And those equations are absolutely empirical and were calculated with normal reinforced concrete, steel and concrete. So they cannot predict, they are predicting a different point there instead of predicting a point in there.
Okay, so the issue is more with calculating the hinge length. Okay, all right,
Yes,
I understand.
Exactly. Yeah. In fact, I'm working, one of my students now, one of my PhD students now, he's very good at coding, and he developed a code. Anyway, I don't want to digress too much, but basically we are developing a huge database and try to come up with new equations for plastic hinge length. But it becomes really complicated because we actually have 2 plastic hinge lengths.
Mm-hmm.
Sorry, I'm taking up a lot of time. But basically we have one plastic hinge length, one plastic hinge here at the bottom, the normal one. But then at some point when all the FRP is debonded, a second plastic hinge forms here. So you have double curvature. You have the first one going like this, and then the second one going like this. It's really, really, really complex.
Okay, no, I understand. Good, thank you.
No problem.
Do we have any more questions?
Rebecca, perhaps I can ask a very short question.
Thank you, John.
First of all, Enrique, congratulations for your excellent work and very nice presentation. I have just a small question about your work is of course very comprehensive. You solved, let's say, a problem. You have provided recommendations for design guidance. You have industrial applications. What's left to be done in the future? Is this a closed topic now, or is there something else that is still to be done?
So there are a lot of uses for FRP anchors. This use is only when the load from the FRP, you want to transfer the whole load or part of the load from the FRP seat into the structure with anchors. But I think what one big portion of research that needs to be done is what happens when you have FRP anchors in the middle. How is that going to change the boundary conditions, the bonding between the FRP seat and the concrete? And I am trying to get some funding for that, but it's really hard because it's going to be an expensive research.
Okay, thanks.
Thank you.
Rebecca, I can ask you a question if you have some time.
Yes, please, Alpha.
Congratulations, Enrique. I think it's a very nice study. I have many questions, but just to ask you. If you look at this slide, on the bottom of the foundation, I can see there's a bend in the anchor. Is it really bent in the bottom or not? Is it straight anchor or bent anchor? Yes,
so
just
the anchor is bent. The anchor is straight, sorry. But to prevent concrete cone, because I was not looking at concrete cone failure, not because it cannot happen in real life, but I was not looking at it. I open it at the bottom. So now the concrete cone is huge. It's basically the whole column. You cannot break it.
Yeah, but in actual life, this will be impossible, right? To do such kind of bent anchor at the bottom of the foundation.
Yeah, that's correct. If it was a real application, it will go down and then the anchor will go in an angle there. Yeah. So it goes back into the core and then your strut and tie is enclosed into that area there.
But I think this is an excellent solution because if you're coming through a slab, you would be able to do this in on any floor except the foundation, I should think. This is a nice answer, actually, I think.
Yeah, for sure. Yeah, they are
doing
doing
a way to get continuity through the slab.
Yeah, we are doing this in New Zealand, and this picture is one example. Yeah, that one. So in here, it's difficult to see because the picture is small and there is a lot of FRP everywhere. But we have anchors in there going into the foundation. This is a basement. And then we have anchors at the top going through the slab and into the floor above.
And Enrique, did you test some anchors with straight anchors to do foundation, or all of them were bent?
You mean
in the column test? Yeah, in the column test.
No, they were all like this because I didn't want concrete failure. My whole PhD was on fiber rupture, so I focused on the fiber rupture.
Okay, because there's probably another issue about slip. In our experience, where we use this kind of FRPs, of course straight, not bent, we had an issue of slip as well, which might have been playing a role on the displacement as well. In your case, if there are some fiber ruptures, not at the same time, but some gradual rupture of the fibers. Anyway, sorry.
Yeah, I did another, I'm not sure how many, I think 8 or 10 columns in the last couple of years with funding from Ravi and Tarek. And we didn't use this method to be a bit more realistic. And we couldn't see any slipping of the dowel out. We were trying different things. We were trying, the paper is in the second round of review, so it should be published soon. We tried to do a bad job at installing the anchors, basically, a bad job at soaking the anchors, but the dowels never came out.
Okay, thanks a lot.
Yeah, thank you.
It's really good to see the questions generated from your presentation, Enrique, and thank you again for your presentation. I understand that it's about 9:30, almost 10 o'clock at night at New Zealand, and we're still going for about another hour and a half. So
Yeah.
if you disappear off this webinar, that's completely fine. We understand.
Yeah, I have to apologize, but I think I will, because I woke up at 5:30 today. My daughter told me it was enough.
I understand. So, but that's been very good that you've been able to accommodate our time frame for this presentation. So thank you for your time. So if there's no more questions for Enrique, I'd like to thank him for his presentation, and we'll move on to the next presenter. So thank you, Enrique.
Thank you. Thank you.
So our next presenter is Omar from University of Queensland. Omar, are you happy to share your screen now for us?
Thanks, Rebecca, for that.
Thank you.
Let's start sharing. Do you see my screen now?
Yes, we do. Thank you.
All good.
Would you? Yeah. You can turn your up to you if you want your video on or not. That's fine too.
I think that is comfortable. I'm not sure.
That's
but
fine.
No worries. Let me start with to thank you actually for arranging this type of gathering, and for all people attending that meeting today. I also want to congratulate the candidate actually for their PhDs, and how much great work actually they have spent in that. So let me start with a true story actually. Before coming to USQ, joining my PhD, it was an opportunity actually to together with my father, and he just asked me a question about my topic, and he said, "What topic are you going to investigate in your PhD?" I was answering, it's a hollow concrete column, and he is, by the way, he is a mining engineer, so he was a bit concerned about that topic, which is actually a trouble actually in mines to have a hollow without reinforcement. And he said, you need to carefully look at reinforcing the hollow part of the columns. And from that actually gathering, I have noticed that as a normal people, if we think to move from solid sections to hollow sections, we are moving towards the weakness. And this is actually, let's say, a general thinking about hollow sections. So from that question, actually, I started to find some answers to convince myself actually, and how I'm going to do like innovation in that part. So I was looking for the current applications on hollow concrete columns, and I found in the industry actually there is a quite applications including bridge beams and ground piles, and even lighting and utility poles. And from that I just concluded that okay, it can be implemented, and there is many people actually before me just like implement the idea. However, it's a little bit limited, and I was looking towards what's the advantages and benefits out of designing hollow sections, and what's the limitation, because I can see there is a limited actually widespreading for that type of application. And from seeing that the cross section itself, you can tell that it's a lighter in weight, and for sure the design will be more economic, and it's a structural efficient, and I have drawn actually many lines underline structural efficient. So I was about to quantify how the concrete column with hollow section inside can give us a reduction in material compared to the reduction in the inertia as well. So if you can see here, the inner diameter and the outer diameter of the hollow concrete, let's say hollow column. So I did a small, like based on the basic engineering, I did just a small quantification of increasing of the inner to outer diameter ratio in terms of material reduction and inertia reduction. And I have found that, okay, you can get a huge or significant material reduction with a very minimal actually inertia reduction. And just like as a case study on 0.5 inner to outer diameter ratio, it can give you a quarter of material reduction and only 5%, let's say, inertia reduction. And after that, I just looked to the stability of the hollow concrete cross sections, and I found that with the slenderness ratio aspect, I can tell that if you increase the inner to outer diameter ratio, you are reducing actually the limit of slenderness ratio. And all of these aspects actually getting me convinced more about that application and to investigate that more. So I just asked myself a question after that: why it's limited? Why it's not widespread actually? Because all the people actually prefer the solid sections over the hollow sections. And from the literature, and actually I just found, let's say, an interesting answer for my questions, starting from the premature failure phenomena for the hollow concrete sections and the low ductility or low, let's say, displacement capacity, you can name. Let's say as an example from one of the scholars in that topic is have done a study on 2010 comparing the solid with a hollow section together, and you can see here it's similar in the stiffness because we are talking about stress to deformation behavior. However, the peak is different. There is a gap between solid and hollow columns at the peak. And after that, the most critical part is the response after the peak, which is related to the displacement and the ductility behavior. And you can see here that the solid section introduced, let's say, a more stable behavior than the hollow column, and the hollow column is gradually reducing the load or the stress capacity. And one of our published papers, actually, we go in deep through describing that phenomena based on the constituent behavior of the column itself. But because in the reinforced concrete column, we have three parts of composing that column, starting from the unconfined concrete cover outside and the reinforcement and the inner concrete core. So by seeing the behavior of the confined core and the unconfined core, we can tell that the unconfined core is shared actually between the solid and hollow sections, and the steel bars have the well-known behavior of plastic behavior. However, the confined core inside is the major actually difference between hollow and concrete column. And you can tell from here the steel bars again and the unconfined concrete is similar. However, the confined concrete is different. And that is due to the absence of the core inside, which actually changed the stress formation inside the core from a triaxial in the solid section to the biaxial in the hollow section. And that actually brief enhancement in the confined core is related to the lateral reinforcement. So let's say by knowing all of these things, and you can tell from the figure is at the right hand side that is closely matching the figure, the experimental figure in the left hand side, we can know now what's happening in the hollow concrete columns with the steel bars. And by telling that the reason is the confined concrete core, that means the confined concrete core is also related on something else, something related to the constituent themselves. And we just digging deep to see how the reinforcement is actually affecting that behavior. And we see, okay, maybe the limited, let's say, strain behavior of the steel, which has a yield strain, may affect that behavior. So after knowing all of these things, we just build them confident on how these sections are behaving. We go like in deep to find another challenge, which is actually a global challenge related to the durability of these sections, especially the RC steel reinforced sections. And all of us know the corrosion and how the corrosion can bring a damage to the RC members. And just to tell, is Australia spending more than 13 billions actually per year on demolishing and rehabilitation and all of these like techniques to get rid of the corrosion problems. And that cost also including the shutdown costs and rebuilding the structures. After that, there is a many actually studies trying to overcome the corrosion. And we can see that there is many techniques on that, let's say starting from galvanizing the steel and coating with epoxy and cathodic protection for the steel bars. However, all these studies just confirm that steel corrosion is reduced, but it's never stopped actually. And on that, there is additional cost to having these techniques. So it's an essential question on what is the alternative then. So all of us know that the newly manufactured, let's say, reinforcement, glass fiber reinforced polymers is now globally accepted as internal reinforcement for the concrete structures. And you can tell from the properties actually of having high strength compared to the steel. And you can see from the figure here how the difference in strength, at least double of strength. And despite of the low modulus of elasticity, it has high strain capacity actually. And you can tell it's at least 1.5 than the rupture strain, not the yield strain, but the rupture strain of the steel bars. And all of these things depends on the grade of the glass fiber bars and the steel bars. And also, there is a high stiffness to weight ratio related to the GFRP bars compared to the steel bars. It's around 0.5 or quarter of steel density. And from like our like recent published work on GFRP reinforced sections, we just let's say replace the galvanized steel bars in the boat round planks with the GFRP bars ones. And the doubt was the initial cost of the bars. However, we were able actually to reduce the manufacturing time by 30% using the GFRP bars, and that was related actually to the density of the bars and the handling process. On the other hand, it's not corroded bars and it's a neutral electromagnetic for such, let's say, special designing. These are not new bars. There is many successful applications in slabs, beam columns, footings, walls, and beam column joints, and many applications after that. So after knowing the alternative now, we were actually, we had to select the critical parameters that we need to apply on the hollow concrete columns actually to find out what's the influence of these bars in the overall behavior of these columns. And doing a massive and a critical review actually on more than 40 research, we found that there is many critical parameters. We limited that to 7 actually main parameters, and we can see here from the figure the relevance percentages of the research actually on these parameters. So we just selected the major or critical ones by waiving the first let's say aspect, which is axial load ratio, which is the applied ratio, the applied load on the ultimate load of in axial direction. And we found that is applied to the combined actions, not to the pure act, because that system is in U. We need actually to find out the influence, a clear influence of these bars on the concrete columns. So we get rid of that, and we get rid of the last two because it's the least relevant to our study. And we relied on the parameters that can affect the constituent of the hollow concrete column. And because of that, we just selected these highlighted 4 parameters. We have designed the experiment based on that. We have selected a range of inner to outer diameter ratio. We have selected different reinforcement, longitudinal reinforcement ratio, and different lateral reinforcement ratio by changing the spacing between lateral reinforcement. And we have selected 4 range of concrete strength within the normal range of concrete, and tested that under pure compression until failure, and using the instrumentation that all of us know actually, which is strain gauges and LVDT. So we can tell from the test results that if the effect of inner to outer diameter ratio was very clear. And we actually surprised by seeing that the increasing of the inner to outer diameter ratio increased the strength and increased the displacement capacity. And that was absolutely related to the properties of the reinforcement, which the steel reinforcement cannot do actually, because the linear elastic behavior of these bars until failure. And one thing actually interesting we saw with the maximum inner to outer diameter ratio column is the failure mode of that column. And you can see here is, so that the failure was inside the concrete core with the longitudinal bars, but without any failure in the lateral reinforcement, which is different actually from the whole previous columns. And we relied on that actually. We study and investigate it in deep to let's say describe that phenomenon by using something called a stress index of the reinforcement and the core. And from that analysis, we just found that if the concrete or if the stress index inside the concrete is more than the stress index of the lateral reinforcement, then the failure will be in the core, not in the spiral. And because of that, we have selected the 0.36 as an optimal inner to outer diameter ratio to be used afterwards in the other samples. And just to show the behavior of that column, and you can see here the linear elastic behavior until the peak, and all of us waiting the drop that we saw before in the hollow columns with the steel bars. But however, you can see how much is stable is that because of the glass fiber bars, and how much it add a displacement capacity to the column. The other parameter was longitudinal reinforcement ratio, and we have done that by changing both bar diameter and bar number. And you can see here the strength enhancement. It's expected now by talking about linear elastic bars actually until failure. And the displacement capacity, you can tell that it's let's say generally increasing or like have some stability. But once you increase the bar number, you also get strength enhancement. However, with a stable displacement capacity. But if you compare between the stable behavior of the displacement capacity to the displacement capacity resulted from bar diameter, you can tell that the displacement capacity from bar number is higher than the displacement capacity of the bar diameter. And we were able actually to innovate something new related to the opening effect between the longitudinal fibers and how those longitudinal fibers contributing to the lateral confinement as well. And that was the innovation in that paper, as you see at the bottom of this slide. For the effect of lateral reinforcement, we have done we have changed actually the spacing between the lateral reinforcement and as expected, we get a strength enhancement in the core and also a significant displacement capacity, and that was related to the lateral confinement concept actually from the bars and from the lateral, let's say, spirals. For the effect of concrete strength, actually there is no strength enhancement was observed actually on the concrete columns with GFRB bars, because we are using the, let's say, that number is normalized, and all the normalization for all type of concrete giving us the same strength enhancement. However, the displacement capacity is reducing actually with the increase of concrete strength, because of the brittleness of the concrete increases with the increase of concrete strength. So after all of these parameters and studying all of these parameters in deep, we just sit and talk to ourselves that this is the time actually to introduce something novel for the design engineers and the research committee actually towards these columns. And we just start to design a theoretical or empirical model to, let's say, capturing all of these, the effect of all of these factors. And we base that model on the constituent behavior of the material, starting from the behavior of the whole column. Let's say if that is the stress strain behavior of the column, and we know the stress contribution of the GFRB bars relying on the elastic behavior of the bars, after subtracting the two contributions, we can find that this is the stress contribution of the concrete. So that concrete behavior is based actually in two critical points, and you can see here the peak point and the fracture point. So we used this theory actually with the existence of the data, experimental data that we have, to initiate some relationships actually to find out these peaks and their locations. And we can see here the model design is based on modeling the concrete itself by dividing the behavior of the concrete by ascending line and descending line, and all of these based on the experimental design parameters. And then by taking the linear elastic behavior of the GFRB bars and combine them together, we can find the total, let's say, behavior of the GFRB reinforced hollow columns. And applying the same theory for the whole columns, we can, we just find ourselves, let's say, validating validating this model actually with all of the experimental data that we have with a good agreement. At the conclusion, we can say out of that work, we were able actually to develop a new structural system on the hollow concrete columns. Imagine that actually after the trial in 1990s, all of the research was towards actually implementing new techniques to strengthen the steel reinforced hollow concrete columns. But having a new design of GFRB bars, we are starting from the same point of 1990s now to open new research ideas and new research, let's say, opportunities actually to enhance the hollow concrete columns, the newly constructed hollow concrete columns, but with GFRB bars. And we were able actually to overcome the related structure and durability issues in the current design of the hollow concrete columns. Also, we identified the major or the critical parameters that are affecting the current design of the hollow concrete columns. And also, we were able to provide or introduce, let's say, a design model to describe the behavior of the hollow concrete columns with GFRB bars. At the end, actually, I would like to let's say, thank TTU and USQ and NSERC for their financial and technical support for us. And I would like to thank actually the assistance that I have got from my colleagues, the research team, and the technician in the Center of Future Material. Thank you all for your kind listening, and thank you for joining us tonight. And I'm open to any question or comment you have.
Thank you, Omar. That was very informative and really interesting to listen to. And a lot of work's gone into that as well, we can see. Are there any questions from the people listening at the moment, please? Okay, maybe I'll start then, Omar. So has this system been implemented anywhere? Is it gone to the next stage of development, do you think, or where do you think it's going to go next?
Thanks for that question. It's a good question actually, because this system is very new system, because no study investigated that like reinforcing the hollow columns in the concrete structures, the hollow one. However, we got a lot of interest afterwards actually in implement these things in Australia here as a utility poles and some other applications. And we extend that knowledge actually to accommodate new students actually working on that. And even we have got interest from scholars on sharing that knowledge and having expanded research, let's say, area on hollow concrete columns. I feel that, and I believe that in the coming years we will be able actually to implement that as a real application.
Okay, and thank you. And have you looked at different types of concrete and the effect there?
Thanks for that question. It's a very important question actually. As I spoke before on the critical parameters that affecting that column, actually we were actually limited to the very critical parameters that we can say this is the behavior or the influence of the GFRP bars in that system. So and also I'm saying that again is it's opening a new gate for research for anyone who wants actually to expand the knowledge on that area.
Okay, thank you. Do we have any questions, please?
Yeah, I'm happy to ask a question. Scott Smith here. Thank you very much for that very informative presentation, and also congratulations on the PhD.
Thanks.
It's probably outside the scope of your work, but I was interested in the capability of this column system to resist lateral loads and to ultimately develop hinges.
Thanks for that question. And actually the next stage for these columns will be under flexure and lateral loads. And there is many theories actually out of that, and how the, let's say, the neutral axis of the load is affecting actually the behavior. And because I'm speaking about when you apply a flexure load to that cross section, you have a compression side and tension side, and how much is the neutral axis close to the compression side and going far away from the hollow part. If you have the neutral axis actually inside the wall, you will get the same theory or let's say the best outcome of these sections. There is a current study on that we are developing now, and hopefully it will come up with a good outcome after that.
Okay, thank you.
Yes.
We still have time for a couple more questions.
Rebecca, can I ask one question?
Yes, please. Thanks.
João Correia. Omar, congratulations for your excellent work.
Thanks.
You mentioned at the end of the presentation, when you were referring to the design approach,
Yep.
you considered the contribution of the FRP bars. I was wondering, did you measure the compressive strength of the rebars and what was the ratio between the compressive and tensile strengths of your rebars?
Actually, after finishing my PhD, I let's say looked for standardizing a test for for GFRP bars under compression, and we have done that successfully. There is a published papers actually out of that. So let's say in terms of strength, it attain, or you can get the same strength as the tensile one if you did the test correctly. The other part is the strain is a little bit lower because the compression is different from tensile actually in terms of the stress transformation inside. And I'm not sure if I answered your question or not, but yeah, there is now let's say a test setup for testing these bars under compression, and as like contradicting the previous research on that, we have get the same strength as tensile strength of the bars.
Well, this is a bit different than the recommendations that are available in design guidelines. But in these, so I'm looking forward to see your results. But in these predictions, did you consider compressive strength equal to tensile strength? This is my question, only for the predictions.
Exactly. So yeah, so that one is, so our study actually was after that, my PhD, but it's related actually to that. It's more about measuring the tensile failure, not the tensile failure, but the strain failure of the bars. And that was quite similar to what we got from the test result of testing these bars alone. It was around 70%, 70% compared to the tensile strain failure.
Okay, thank you, Omar.
Nice.
Are there any more questions from the audience? Okay, I think if you all join me, and I'm sure everyone will agree, to thank Omar for his presentation. It's very well presented and informative, and thank you for your time.
Thanks, Rebecca, for that. Thanks all.
Thank you. So our next presenter is Dr. Marco Rossini. Now, Marco, are you still here online? We potentially may not have been available for a short period of time.
I'm connected now.
You're connected, wonderful. So you'll be able to share your presentation with us. That's great. Or do you want us to...
Yes, I don't have a decent setup to make the presentation myself right now. I will be more than happy to answer my questions, but I'm really sorry about that.
Okay, so just to explain, Marco's kindly pre-recorded his presentation and has made that available to us. So in a moment, Scott will share his presentation for us, but Marco is here online and he'll be able to answer our questions at the end. So Scott, I'll pass on to you to share that presentation, please.
Okay, will do.
Good evening, everyone, and thanks for this opportunity to present my work today. And
can I just check, can everyone hear that okay?
Yes, we can hear that. It's a little bit muffled, but I think it improves as we go.
Okay, I'll turn the volume right up on my end. Okay, take it away, Marco.
Dr. Marco Rossini, and the title of my dissertation that I defended almost 1 year ago at the University of Miami is FRP reinforcement for pre-stress concrete applications. I don't think that FRP requires a lot of introduction in this context, but I want to start by discussing what is the significance of this research and what is the problem we want to address. The problem is corrosion of our infrastructure. We know it is an issue from the cost perspective. Just to give a figure, the annual cost of corrosion for highway bridges in the United States amounts to $8.3 billion. But we know that corrosion is also an issue from the safety perspective, with nine major bridge collapses caused by corrosion since 2014. Finally, corrosion is also an issue from the sustainability perspective and for the resilience of our infrastructures and coastal communities. And we know that we can mitigate these issues by using non-corrosive reinforcement. So we believe that the solution to this problem, or part of the solution, can be found in fiber reinforced polymers. Carbon has been widely used for pre-stress application in the past, whereas glass has been used for reinforcement applications. Whether glass can be used for mild pre-stressing application is the question we want to answer today. In order to answer this question, of course, we need to fill some knowledge gaps, and we need to bring some creative contribution to do so. This dissertation is made up of 3 separate studies, but closely related. The first one deals with the current state of the practice in dealing with pre-stressing with carbon FRP. The second one proposes an alternative solution in the form of pre-stressing with glass FRP. The third study fills a fundamental knowledge gap that prevents using glass in pre-stressing application at the moment, and that knowledge gap is in creep rupture behavior. In order to conduct this research, of course, we needed some money. I was lucky to be the author of 2 successful proposals for funding. The first one for US federal funding through NCHRP IDEA program. The second one for seed funding in a project that involved also the University of Houston, the University of Texas at Tyler. Let's move on to the first part of this study now, that deals with pre-stressing with carbon FRP and focuses in particular on a specific structure that we call the innovation bridge. This bridge is simple. It's made of 2 precast pre-stressed double T-girth, a cast-in-place stack, cast-in-place caps, overcast piles. It is 20-meter long and is designed as a pedestrian bridge. So what we call it the innovation bridge because it, in its simplicity, is also iconic. It is entirely reinforced using FRPs and non-corrosive reinforcement. We have carbon for pre-stressing, glass and basalt for reinforcement application. During the construction phases of this bridge, we noticed that there were no real issues in handling reinforcement, being it made of glass or basalt, as long as it was not pre-stressed. Here you can see the installation of pile cages. They were very light and easy to install. Here you can see the deployment of some innovative shapes in the form of closed stirrups made by filament winding. But finally, the culprit. There were indeed some issues in applying pre-stressing to carbon FRP. It is a very effective technology, but also a very complex one. And we will have time to dig into all the specificity of these issues. But first of all, let's have a look at how we approach the design of the structure. When I first approached the design of the innovation bridge, I was just a young PhD student, and I noticed that there were a lot of different codes and standards for dealing with the same issues. I decided to come out with what I like to call a unified design approach that covers reinforced concrete and pre-stressed concrete with FRP, that takes off from ACI standards, integrates them with ASTM as material specification, and looks at AASHTO bridge design specification for everything that is bridge related. All keeping in mind that consistency is paramount if we want to have wider deployment of FRP reinforcement and make practitioners comfortable with this new technology. All this work was very helpful in allowing me to design the innovation bridge, also was instrumental to help us develop the second edition of the AASHTO Bridge Design Guide specification for GFRP reinforced concrete, guide that has been published in 2018 that went in filling one of the fundamental knowledge gaps that existed in design guidance for practitioners, at least in the bridge industry. For what concerns design provisions, they are quite classical, as long as you provide all the adequate reduction factors for all the respective ultimate and serviceability limit states. You can design using FRP as an alternative material with respect to steel. Different standards define this different safety factor in different ways, but as long as one takes a consistent approach in looking at different standards, this consistent conceptual framework can be used as a tool to identify areas of potential improvement and areas of further research. For what concerns design equation, there's nothing really new. The fundamentals are always the same, the sections remain plain, and the rest follows from there. Let's move to a more exciting part of this presentation in order to make sure that our design approach was reasonable and made sense and was working. We have to test and monitor our structure. In order to do that, we placed quite a number of instruments in our bridges, including vibrating gauges, dial gauges, and serving targets for monitoring during in-service conditions, and we performed a series of load tests. First of all, here we see the strain monitoring in our strength during pre-tensioning and during the first years of service, and we see quite a good agreement with expectation, and then load testing. The first one was performed at the precast site One of the two double T girders was loaded with a crane up to 75% of its net cracking moment. And here you can see quite a good agreement between our theoretical expectation and the actual behavior that we recorded on site. We were also able to monitor the performance of the girders during concrete pouring because we knew the weight of concrete and we had the structure instrumented. And also in this case, you see quite a good agreement with our expectation. Finally, when the structure was completed, we brought the truck on site. We load tested the final structure. And also in this case, even though we are at a lower order of magnitude because now the structure is much more stiff, we have very good agreement with our theoretical expectation. And we went back again, this time with 3 trucks, and this time more than 1 year into the service cycle structure. Also in this case, you can see from the figures on the right that both in terms of deflections and both in terms of strains, we have very good agreement with our theoretical expectation. This confirms our conceptual approach to design with FRP being it pre-stressed or reinforced structures. And this concludes the first part of this dissertation, when we discussed the development and the deployment of a unified approach for design. And when we first identified some issues in the deployment of carbon FRP as opposed to glass FRP for reinforcement application. Let's move on to the second part of this dissertation, when we dig into the technological issues that were experienced using pre-stressing with carbon FRP, and how we want to address them using PES. First of all, the issues. As I said, carbon pre-stressing is a very effective technology, but is also a very complex one for a serious reason. First of all, carbon is an expensive material. It comes at 4 times the cost of traditional steel strengths. It's expensive, meaning that it has a relatively high pseudo-Poisson ratio that can cause concrete to spoil and crack when we release pre-stressing. It's also a complex technology that requires large anchors, requires splicing, typically proprietary technologies. Finally, it's brittle, and this can be an issue both during constructability for safety concerns and also during the service type of the structure, being anything expected of course. If you think about it, you can mitigate all of these issues by reducing the level of pre-stress that you apply to your strengths. If you reduce the level of pre-stress, you can use simpler anchors, smaller anchors, and you can achieve still high constructability. You can limit cracking in your concrete because that is directly proportional to the level of pre-stress that you apply. And you can also achieve safer pooling because now you're working at a level of pre-stress that do not represent an hazard for people working outside. But of course, if you reduce the level of pre-stress in your structure, you cannot target all the structural elements that are out there. You cannot target bridge girders, at least not at this stage. We are focusing on those elements that require the least amount of pre-stressing, but also experience the highest degree of corrosion. And these elements, in our opinion, are substructural elements, bearing piles, sheet piles, particularly in coastal areas. If the solution that we want to adopt and they reducing the level of pre-stress in our structure, we need a material that makes it reasonable from both the cost perspective and from the mechanical efficiency perspective. We believe that this material is glass, particularly in the form of a 7-wide strand, of which you see a prototype in these pictures. Glass is more economic than carbon. It comes at 1.5 times steel, the cost of steel, and is going down as more manufacturers are coming into the game. It's a more efficient technology for pre-stressing because it has a lower modulus that results in lower pre-stress losses. If we reduce the level of pre-stress, as already said, we can use simpler anchors. And also glass is a pseudo-ductile material in the sense that it can achieve larger displacement with respect to carbon at lower level of stress. But no one has ever tried to do this on the field and not even in a laboratory, so we need to collect some experimental results, and we need to do our homework to see if this is actually feasible. Our experimental study focused on verifying if we can couple a traditional pre-stressing anchor used for steel strength with our prototype glass FRP strength. Here you can see how we grabbed our strand with traditional anchors, we pulled it, and we see at which level of load was breaking. You see from the diagram on the right that even though we are dealing with a prototype material, we are treating it in a pretty bad way because we are coupling it with bare steel. We are getting quite consistent behavior at 56% guaranteed tensile strength of our raw material itself. And this is a level that can allow us to achieve effective pre-stressing. But we don't just need our material to be pulled, we need it to maintain its pull for quite some time while we pour our concrete. We wait for it to harden, and then we can release it, because remember, we're dealing with pre-tension right now. In order to verify this possibility, we conducted some pseudo-creep test. Why we call it pseudo-creep? Because it's the displacement that you see in the diagram on the right is not only caused by the inherent material based creep that we have into our geometry strand, is mostly caused by slipping and by phenomena that are localized and happening at the anchor location. Of course, if you have slipping at the anchor location, you should expect some load losses. And that's why we also conducted some pseudo-relaxation tests that were aimed at measuring these losses that amounted to up to 20% of the initial load that we were applying. And also in this case, and we were able to measure this by applying an extensometer, we noticed that most of the losses were, or at least a good portion of it, was caused by slipping at the anchor location. Now, this level of losses, 20%, even though on a short length, was deemed excessive to achieve effective pre-stressing on site, and so we decided to try alternative pooling procedure to make it feasible and more efficient. In trying different alternative procedures, you should keep in mind that sometimes you deal with very refined pre-stressing facilities, sometimes you are just in the jungle, as you see from the picture there, and that's a very typical pre-tension yard in South Florida. The first solution that we tried is the one that I already mentioned. We just load our strand up to the level that we want, then we release it and we see how much losses we get, and that's 20%. That's too much, so we decided to maintain the load applied in the load control before switching to displacement control for a while, from 1 minute to 15 minutes. We see that this solution is effective in reducing the level of losses that we have, but still it's not enough, and also it is a very difficult procedure to deploy in the field. So we propose an alternative procedure that is actually pulling our strand up to the level that we want to, let it rest overnight for at least 12 hours, go back to the field, pull it again. At this time, we pour our concrete, and then we let it rest for 12 hours before for concrete to harden, before we release our strand and transfer pre-stress to our structure. This proved to be the most effective solution, and even though it's quite time-consuming, it's something that a lot of precasters are still familiar with, because it used to be standard procedure before low relaxation strengths were common. With this, we've answered the fundamental question that where can we actually pull our glass FRP using traditional anchors, and we saw that we can do that. Our material is able to maintain that pull, and we can also develop procedures to reduce pre-stress losses, sitting losses at levels that are reasonable to achieve efficient pre-stressing. One last question remains is whether our structure, after we have built it, after we've built our structural element, is able to withstand that level of pre-tension and sustain load through its entire service life. In order to answer this question, we need to look into pre-rupture behavior of glass FRP. First of all, let's see where we were before undertaking this study. ACI was saying, and is still saying, that you can have a sustained load in your glass FRP reinforcement equal to at most 20% of the design strength of your material. We were able to raise this limit a little bit while publishing the second edition of the actual design specification in 2018, and we raised this limit from 20% to 30%. But now we will see that through this study, we see that at least in some material system, this limit can be as high as 45-46% of the design strength. In order to show this, of course, we had to conduct some experiments. Here you see our pre-rupture beds. This test was, we conducted the 50 tensile test, 50 pre-rupture test on 2 different types of bars. Here you see the two different types of bark with different surface, the surface preparation. But first of all, before looking into the experimental results, let's have a look at what is the conceptual model that we built in order to predict what is the temperature strength of this material. Because in addition to lack of experimental data, we noticed a lack of a conceptual background in order to interpret this data. We know that we can plot time to failure points in a logarithmic diagram. What is crucial in this slide is to notice that our interpolant line must intersect the ultimate tensile strength of our material at time 0. Otherwise, our modeling is not consistent. Because if you think about it, a tensile test is nothing but a very short pre-rupture test. Interpolating lines, interpolating points is not enough to predict the design value. We need to account for variability in our numbers, and we have scattered both along the time axis in our types of failure and along the strength axis in the strength of our material. Accounting that through statistical modeling, we can shift and rotate our main interpolation line and define a characteristic interpolant that takes care of 95% of our failure points. But 95% is not enough. You don't want 5% of your structure to fail when you design. You want much less. In order to do that, you need to apply a gamma factor, a safety factor, that shifts your characteristic line down to a guaranteed line that is defined in a consistent way between ACI and Eurocodes and takes care of 99.9% of your failure points. Let's see how this translates in actual numbers. Let's see if this model actually worked on the number of the data that we collected. Here you see our statistical modeling. We used a Gaussian distribution for strength and a Weibull distribution for time to failure. You see that in both cases we have quite a good agreement and matching. And here you see our temperature strength prediction for the type 1 bar that you see represented on the left. You see that by simply interpolating our points, we get a strength that is at approximately 80% of the guaranteed tensile strength, reading numbers on the right side of the diagram. By accounting for statistical variability, we shift that down sensibly, and we cover all the, and we do not intersect any of the rupture points. By applying an additional safety factor, we get to the value of 0.46. That is more than 50%, the limit that was that is currently imposed by ACI, and would allow for a much more efficient and effective design against rupture, reinforced concrete structure, and increased stress concrete structure. The same results we get on type 2 bar, even though we're dealing with a different kind of surface preparation. And this is interesting because it may imply, and needs to be confirmed on a larger data set, the type of surface preparation that we have in our bar does not really affect their rupture behavior. This answers the third question that we were asking ourselves, that is whether our pre-stress structure with glass FRP strand is able to withstand the level of pre-stress that we apply through its entire service life, and the answer is yes. Just to summarize what we saw, we had a look at a new concept for FRP pre-stressing using mild pre-stressing in glass instead of carbon. Why we looked at this? Because we want to address the problem of corrosion, and because we want to address some inherent limitation of the current technology. How we investigated this issue? First of all, we assessed the current state of the practice. We developed a new concept to overcome the limit of the current state of the practice. Produced empirical evidence to support our idea, our proposal, and we filled the modeling and knowledge gap in the rupture behavior of glass FRP. In doing this, we were also able to provide design guidance, publishing the second edition of the Ashton Reed Design Guide specification, and providing support for the development of the new ACI building code for GFRP. All of this is not just for the sake of research. This technology is actually working, and we have been building and installing 2 partially pre-stressed piles with GFRP in a bridge in South Florida. This is the first demonstrator for the technology in a bridge owned by the Florida Department of Transportation. With this, I've concluded my presentation. I just want to acknowledge our sponsors and our partners. And I want to thank you for your kind attention. And if you have any question, I would be more than happy to answer them.
Thank you, Marco, for your presentation. I know you're on here online now. It's really good to see the research with pre-stress FRP progressing as it is, and the real impacts that you're making with those prototype examples, and also some applications in the field. Before I ask any questions, is anyone else out there that has a question for Marco? Just going to turn my video off. No questions, so shall I start then? So Marco, you identified the challenges with carbon FRP and the issues with successfully anchoring the tendons, and so
Yes.
that influenced your investigations into GFRP. Do you see the GFRP replacing at some stage conventional high tensile steel strands, or is it where do you see the applications being more useful?
Well, let's say that we don't see in general GFRP strand replacing steel strands in any kind of application, but we do see raising interest in those applications that require a lot of corrosion resistance. As a matter of fact, as you mentioned before, we are quite happy of the impact that we're making in South Florida. We have now the Florida Department of Transportation that is issuing guidance and policy document requiring the use of FRP and non-corrosive reinforcement in those very corrosive applications with seawater and so on.
Okay.
So not for all application, but for sure we see a lot of requests for those applications that have a lot of corrosion exposure.
Okay, that sounds good. And because the tensile strength of the GFRP, I mean, you can't get as high a value with high tensile steels or carbon. So I suppose that's why you're using the partial pre-stressing methods.
Yes, that's true. First of all, we are targeting those applications that require lower level of pre-stress. So we're looking at the bearing piles and the sheet piles and in general substructures that are also the ones that are mostly exposed to corrosion, at least in South Florida. We don't see this technology, at least at this stage, to be applied for say one in bridge girders, maybe in flat slabs in the future for shore span bridges. Yeah. But let's see that this is I would say another tool in the toolbox. So there are some applications where this is more cost efficient, and in some cases more effective because it's more efficient also from the point of view of pre-stress losses, but not all the applications, let's say.
Okay. Yep. Thank you. That's
good.
I
have a question for Marco, if I can.
Thank you.
Sure. Please go ahead.
I think it's interesting to see that you're really pushing out the potential creep issues on glass, which I think is good because that's obviously a significant limit. But if I understood, is all the creep testing is done in air, and so it doesn't address potential effects of creep on bond. And these are still bonded systems, right? These are obviously they are strain issue. Do you think you can keep moving out the creep numbers? You know, you're 30% in the ash toe, and I think you were proposing close to 50, right? Was that what I saw?
I would say that we are in this two rebar system, we saw 46. I would say that we have run the numbers on a much larger data set that involves a much larger number of manufacturers, and we saw 40. But if I see the point that you're making, I would say that we are going as high that we start to actually look at the effect of creep on the bond, and I do agree on that we're getting at that point.
Because the bar tested in air, I mean, it's the same thing with fatigue, is tests in air and tests in concrete are potentially very different results. And so that would be a concern that I would have. And I would encourage kind of looking at that issue too. And it would be a difficult issue to look at and much more expensive, I appreciate.
Yeah, I totally agree. We did some structural tests. We weren't able to do long-term structural tests, but at least we did some structural tests before going to the field. And we do have some spare piles that we're hoping will be able to do some long-term testing, but that of course depends on funding and on the future, let's say. But I do see your point, and I do agree that we're getting at that point where creep and bond are starting to become something that we need to look at into details.
Yeah, they're interacting significantly, so that would be a concern.
Yes, yes.
All right, thanks.
Yes.
Yeah, Scott Smith here. Look, thank you very much, Marco, for that really informative presentation, and congratulations. It was really encouraging to see the traditional metallic anchors performing well in your studies. So, did you develop a feel for, say, how forgiving that system is, given that traditional steel tendons, you know, there's as an isotropic material, but with the FRP composites, it's not. Did you develop a feel for how forgiving and maybe how far you can push those traditional steel anchors before you might need to go to something more customized for FRP?
Mm-hmm. Yes, we've stayed on empirical research as of now. We know that we can pull actually our material up to 55% as instantaneous pull, and then we perform some both sitting losses and what I call the pseudo creep rupture with anchors in place. And we know that at least over, say, 24 hours, we can stay at around 40% of our of the guaranteed strength of our material. And that's not as high as where we can get with steel strands, but still is enough for the kind of application that we're targeting. So the whole point is to not push the material too much, so we don't make the technology too complex. Of course, for those applications where we need a lot of pre-stress, we need to look at something more complex, and we get back in the loop of having to deal with complex anchors and so on. But then it's unavoidable.
Yeah, thanks, Marco. So that's good.
I don't know if this.
Yeah, that's good. Thank you.
Okay, thank you.
Do we have any more questions for Marco? Okay, we have one more presenter, but before we do, I'd like to again thank you, Marco, for firstly being able to accommodate this presentation by doing your pre-recording. I think that worked very well, and also for being available for the question time. So thank you. And if there's no more questions, I'm going to introduce the next speaker.
Thank you for this opportunity.
No worries. Thank you very much.
Just wanted to say thank you. Bye.
You're welcome. So our last presenter for this session is Gui Wan from Tsinghua University. Gui Wan, are you available there online?
Yeah, I'm here.
Good. Hi. Can you share your screen for us and your presentation?
Yes, of course. Okay, can you see my PowerPoint here?
Not yet. Yes, we can. Thank you.
Okay.
So when you're ready, please start your presentation and welcome.
Okay. Thank you, Chairman. Good evening, ladies and gentlemen. My name is Ziyuan Wang, and I got my PhD degree from Tsinghua University, China, in 2019. And my supervisor is Professor Feng Peng. I'm so honored to have this opportunity to present my work during my PhD study here. Well, as you can see, my topic would focus on the study of axial compressive behavior and seismic performance of RC columns reinforced with FCCR. My presentation today includes the following three main parts. And firstly, I'll give some introductions on the background and motivation of this research. Well, as we all know, the collapse of the columns is considered as the most critical failure mode in the reinforced concrete structures during an earthquake. So how to postpone or prevent such failure patterns include the crashing or spalling of the concrete and rupture of the steel hoops and the local buckling of the vertical bars. Well, it's a critical issue for improving the mechanical behavior of the RC columns. So the very initial motivation of this research is that we want to come up with some ideas that can be conveniently accepted and used in the practical constructions to get a much stronger column. Well, the utilization of the high-strength materials is a convenient way to improve the load capacity of the column. However, by directly adopting these materials, it is still hard to improve the ultimate performance of the columns due to the disadvantages of these materials. And on the other hand, the confinement of the concrete has been proved an effective way to improve the ductility and anti-collapse capacity of the columns. But the traditional CFFT or other confined concrete columns configuration is sometimes hard to be used in the practical buildings due to the construction problems. So based on these concepts and problems, a novel component named FRP confined concrete core encased rebar, abbreviated as FCCR, is proposed in the present dissertation. The FCCR is composed of the internal high-strength steel bars, the field high-strength concrete, and the external FRP tube, as shown in the figure. Well, for this component, the compressive strength and ductility of the field concrete are enhanced due to the lateral confinement effect of the FRP tube, and cracking and spalling of the concrete is then prevented. Thus, the local buckling of the rebar can be prevented under compression due to the lateral support of the concrete. So the problem of the strength loss of the high-strength rebar buckling and the poor ductility of the high-strength concrete can be avoided. In this way, this new component shows great mechanical performance under either compression or tension, which can be regarded as a high-performance composite bar. And by replacing ordinary bars in columns with FCCR, part of the concrete regions can be effectively confined. And FCCR can perform as a high-stress skeleton to enhance the column's mechanical behavior. So this new component can be flexibly used in different parts in the traditional RC structures, which highly widen the practical application range of the confined concrete. And this slide shows the technical root of this research. At the component level, the buckling resistance effect and the axial compressive behavior of the FCCR is studied. And at the column level, the compressive and seismic behavior of the composite column is studied. And finally, the design method of the FCCR and the composite column is proposed. Well, it can be seen that for this newly proposed configuration, this dissertation did quite systematic work from the component to the column, from experiment, numerical simulation to theoretical calculation method. And in this procedure, from the angle of the science research, several case scientific problems is encountered and solved. And from the point of view of technology development, the proposed design method can give the advices to the practical use of the FCCR and the column. So in the second part, I'll give some brief introduction on the researches and gains of the dissertation. And in chapter 2, the yield condition of the internal steel bars under compression is firstly studied. And experimental study on 42 specimens under compression were carried out. The axial load were applied only on the internal bars in order to figure out the buckling resistive effect of the FCCR. And according to the test results, all the specimens illustrate a quite similar failure progress. The peak load can reach or even exceed its yield strength for bars with a relatively large slenderness under axial compression. And based on the experiment, the finite element model is then established by using software AppCurves. The failure progress and the low displacement curve of the specimen obtained from the FE model agrees well with the test result, and additional parameter studies were also carried out. And finally, based on the criterion of the rebar yielding, the basic configuration rules of the FCCCR is proposed. As long as the FCCR meets the requirement of the proposed minimum effective area ratio, the yield of the embedded rebar under compression can be ensured. Well, in the next chapter, the axial compressive behavior of FCCR is studied. Well, 9 specimens are tested under either monotonic or cyclic compressive load, and test result indicate that the ultimate failure of the FCCR is controlled by the circular fracture of the FRP tube. And the low displacement curves of the specimen show a typical bilinear ascending behavior, which is quite similar to that of the ordinary CFFT, the concrete filled FRP tube. Well, in order to predict the compressive behavior of the FCCR, six confined concrete models were chosen to calculate the low displacement curve. However, traditional theory of the FRP confined concrete illustrates obvious deviation in predicting axial compressive behavior of FCCR. And we believe that the reason of this phenomena is that the thickness to diameter of the FRP tube in FCCR is much larger compared with the ordinary CFFT, resulting in a much higher confinement stiffness. And it can be seen that most of the data used to calibrate the concrete models have a confinement stiffness less than 2000 megapascal, while that of the FCCR reaches around 3000 to 4000 megapascal. So in order to make a more precise prediction of such heavily confined concrete, we collected test data of 56 FRP confined concrete specimens in the previous papers. And by analyzing these data, the popular analysis-oriented model proposed by Jiang and Cheng is updated in this dissertation to ensure the accuracy of the heavily confined concrete. And by bringing this update model into the AppCurves, the finite element model is also established and calibrated by the test result. Moreover, the influence of the diameter and the location of the internal rebar is also analyzed and discussed. Well, in chapter 4, the compressive behavior of the columns with FCCR is studied. FCCR reinforced 8 FCCR reinforced columns were tested under cyclic axial compressive load. And the main parameters include the amount and diameter of the FRP tube, as well as the stirrup spacing. But test result indicate that the existence of the FCCR will change the final failure mode of the column. Due to the test, during the test, the local buckling of the vertical bars and rupture of the steel hoops and crushing of the core concrete is not observed. But it is noticed that the overall buckling of the FCCR has become a critical issue and shows obvious influence on the compressive performance of the column. Well, the low displacement skeleton line, peak load capacity, and ductility capacity of the composite columns are summarized in this slide. And with proper FCCR and the stirrup arrangement, the low displacement curve of the columns can illustrate a second ascending branch, resulting in obvious enhancement of of load capacity and ductility. Well, in order to calculate the performance of FCCR in the columns, the overall bulking and the influence of the lateral support should be figured out. Firstly, the finite element analysis is carried out. Then a numeric method and a cross-section strip method are adopted and programmed in the software MATLAB. And then a simple method by combining the load capacity and the modified Euler load is proposed. Well, by the comparison of these three methods, the accuracy of this simplified calculation method is then verified. So at the end of this chapter, the cross-section superposition method is proposed for calculation of the load displacement performance of the column. And the result showed a good agreement with the test result. Moreover, it is noted that the load provided by the FCCR is the main part of that of the columns, which surely played as a strong skeleton as we expected. Well, in the chapter 5 and 6, seismic performance of the FCCR reinforcement columns is studied experimentally and numerically. Well, experimental study was firstly carried out under the combination of the constant axial load and the cyclic lateral load. Well, during the test for columns with FCCR, no local buckling or of the vertical rebar or severe concrete crush is observed at the plastic hinge zone. All the composite columns illustrate a vertical splitting failure pattern, which indicated that the bond between the FRP tube and the outside concrete cover has a great influence on the utilization of the FCCR. But this failure mode will only influence the column's behavior at a relatively large lateral drift ratio, but has little influence around the peak point. And beside the failure mode, the bearing capacity and high static performance of the columns were obtained and compared. Well, by adopting some bond strengthening configuration between the FRP tube and the concrete cover, such as apply a quite thin FRP jacket to the columns, the seismic performance of the column can be enhanced significantly and show a quite excellent high static performance. Well, due to the bar buckling resistance and the confinement effect of the FCCR, the composite column specimen illustrate a higher peak load and a better ductility and energy dissipation capacity under seismic load. And based on the test results, software OpenSys is used to establish the fiber section model of the columns. But due to the vertical splitting failure mode, slipping exists at the FRP tube concrete cover interface. So the plan section assumption is no longer strictly followed. Therefore, FCCR and external concrete cover are modeled separately in OpenSys, and a series of spring elements are established between these two parts of the model. And then the accuracy of this model is then verified by the experimental result. Based on this modeling method, the influence of different parameters such as the axial compression ratio, the bond behavior, and the arrangement of the FCCR and etc. is analyzed and discussed. And in the chapter 7, the design method of the FCCR and the column is proposed and discussed. Well, one of the critical principles in the design of the columns is that we did load capacity check at two types of ultimate state. Well, include the ultimate strength of the ordinary concrete, 0.0033, and the ultimate strength of the confined concrete, 0.01. If we consider only the ordinary concrete ultimate state only, the concrete confinement effect will be highly underestimated. And for flexure design, the equations for calculation of the MN curves are proposed and calibrated. And finally, a design example is executed. It is indicated that the columns can be designed with a smaller section area and less steel reinforcement by equipping FCCR. So finally, to sum up, here are some major conclusions or contributions of this research. And firstly, a novel component named FCCR and the corresponding composite column is proposed, and the main mechanical behavior is studied. Well, as for the science problems, the buckling behavior of the internal steel bars in the FCCR is figured out, and the columns model is updated. The concrete model is updated to ensure the accuracy for heavily confined concrete. The interaction effect and the overall buckling behavior of the FCCR in the columns is figured out. And from the point of view of the technical problems, the basic configuration rules of the FCCR component are proposed. A superposition method is proposed to calculate the axial load displacement behavior. A separately modeling method is proposed to simulate the column seismic behavior in open seas. And finally, the design method of the component and the columns is proposed. So here are some papers accomplished during my PhD study. And that's all for my presentation today. Thank you.
Thank you, Gui Wan. Very informative, in-depth presentation that you have provided us today on your PhD topic. So thank you. Do we have any questions, please? Okay, I will start with a question. So how difficult is it to manufacture the FRP concrete filled bars? Is it something, did you make them in your laboratories, or how are they manufactured?
Yes, we made it in our lab and by some workers and me. So it is quite easy to manufacture such components. We just have to put the rebar in the FRP tube and fix the position of that FRP of the internal steel bars and fill the tube with concrete. It is quite the same with the cast of the concrete filled FRP tube.
Okay, but you're looking at much.
Rebecca.
Sorry?
Could I follow up on your question, Rebecca?
Yes, please. Thank you.
What about the weight of these things, and how did they get erected in the field? I mean, this seems to really change the column reinforcement erection process significantly.
Yes, the weight of this component.
Yes.
Sorry.
I mean,
Yes,
how do you handle it in the field? It's not a bar anymore.
Yes, it's not a bar anymore, but it can still use as a bar. The dimension of this component is relatively small compared with the columns. And if we want to use a larger one with more region of the concrete to be confined, and we can also use the workers to position to fix the position of the FCCR into the columns. And I think there is one picture that can show the position
Well,
of
I'm thinking about how do you handle this in the field, because even though it's very, very heavy, I suspect it is also reasonably flexible when I'm handling it as I would handle a bar and place a bar, in which case is there not damage during handling and so on and so forth.
Well, yes, we can use some machine to do this work, and also we can have it done by some workers. I think it's not a problem, since that in the lab we can did this work. So in the field, I think it is also possible to do this work by the constructor.
So how heavy is a 4-meter long piece of 100mm FRP confined bar? I suspect it's fairly heavy.
Well, yes, but compared with the CFST, compared with the steel tube, it is quite lighter compared with the steel tubes. So we can also use the steel tubes in the columns. So it is not a problem in construction field.
Okay.
Thank you. Do we have any other questions from our audience, please?
Hello, can everyone hear me?
Yes.
Thank you, Mr. Wang. Thank you for your presentation. What I'm curious about is that how do we deal with the junctions? We have seen the FCCR great performance on earthquake. How do we consider how do we to try to form the junction?
I'm sorry, how do we deal with the
nodes in the structure, the junctions?
Oh yes, to the joint of this kind of columns, we don't let the tube to go through the joint of the columns and the beam. So it's only the steel, the internal steel bars to anchored in that area. So there won't be any difference with the normal RC structures.
Okay, but does it imply that the joints will be a little bit weaker compared to the beams or the columns? When it comes to earth engineering design, we want that we have got strong joints and less strong or a little bit weak beams or columns. So does it correspond with that principle?
Yes, but at the joints there are there are a lot of steel reinforcement, as you know, and a lot of stir up and vertical steel reinforcement. So it is quite impossible to let the let the tube go through the joint. So for the convenience, it is quite easier to cut the tube at the joint, and the main cause of the main problem of these columns is not at the joint, but the bond behavior between the FRP tube and the outside concrete. So I don't think the joint is a problem in the practical use of this kind of component. And what we concern more is maybe in the future is the shear capacity and the bond behavior of the FRP tube and outside concrete.
Thank you. I think that such columns can be produced in factories, and perhaps it could be really useful in prospective prefabricated buildings. I think this is really promising.
Yes,
Thank
yes.
you.
Okay, thank you for your questions so far. They've been very informative. And do you have any more questions for our presenter? I'm just conscious that we've just clicked over the 2-hour time frame, and I think we've done really well for everyone to remain on this webinar. So I thank you all for your time and patience up until this point. If there's no more questions, I'm going to thank Wei Wan for his presentation and making his time available. And I would also like to thank all the 4 presenters that we've had today. I think I'll just share my screen if I can. If Wei Wan, if you unshare your screen for me, that would be good. So we had our 4 presenters, and from quite very different topics and from all parts of the world. So, and I think it's shown sort of the breadth of work and areas that we're all working on FRP in construction, for construction materials. So I thank the presenters for that perspective that it's provided us today. I'd actually like to pass over to our president of the IIFC, Professor Scott Smith, who I would like to ask him to provide the closing comments for today, and also to thank him for providing this webinar platform available to all of us. Scott, are you available? Would you like to say some closing remarks for us all?
Happy to say a few words. Look, thank you, Rebecca. Look, first of all, thank you very much to our 4 speakers. Really appreciate the effort that you've gone throughout your PhD studies, and also the effort that you've put into presenting your work here today. And you've shown a real mastery of your topics, and that's really where we want to land at the end of a PhD. And I'd like to say the quality of the work that we're seeing in our community through your work is excellent, and it's very encouraging to see the quality of this work continuing into the future. I'd like to thank Rebecca for hosting this session, and also for chairing the Best Thesis Awards Committee. And I would also like to thank the members of the judging committee, Joao, Alpa, and Karim. And I'd like to thank everyone who was able to join us on this call. Unfortunately, there isn't a single time that's going to suit everyone around the world, unless you don't sleep, which actually I suspect is quite a few of us. But nonetheless, look, thank you everyone for dialing in. This session is being recorded, and we are going to be posting this on the IIFC website. We felt this was the best solution to run the Best Thesis Award competition, and to give closure to our speakers, and rather than wait until the CICE conference is going to be run next year. So that's will do for my concluding remarks. And look, I thank you all again, and please everyone stay safe and stay healthy. And I really look forward to seeing you all at an event, hopefully face-to-face, in the future. As a minimum, I hope to see you all at Alpa's CICE 2020/2021 conference in Turkey next year. Thanks again all, and good night, good day, good morning, wherever you are.
Thank you, Scott, for closing that for us. And I'm just going to ask the judges to remain on this webinar, please, and just wait a moment while everyone says their goodbyes, and yeah, we'll leave it at that. But thank you again, as Scott said, for everyone for your participation, and I've really enjoyed listening to everyone's to the PhD students present today. So thank you. If there's no more questions, I'd like to say goodbye.
Thank you all.
Okay, so we have a couple of people still left. I've got Scott, Joel, Alpa here, and then there's a few other people still online. I just might wait until it's just us left, unless Scott, you want to send us a separate invite. I don't know.
Yeah, I can do that, Rebecca.
Might be easier. Is that okay?
Yeah, no problem. I'll send that shortly. I'll stop recording now and sign off.
Yeah, is that okay with you, Alpa?
Yeah, sure.
Yep, and Joel, is that okay?
It's okay.
All right, give us a chance to get a glass of water or something. Thank you.
Okay.
Bye-bye.